Okay. Can you hear me? Great. Um, Sorry for the confusion there. We're still debugging a few things apparently here. But thank you everybody for hanging in there and joining us for our first SIG webinar of the year. Just as a reminder, the overall aim of the SIG webinar series is to connect mathematicians to computer scientists, to geoscientists, among others. This year's seminar series begins with topics in geodynamics, which aim to both broaden our community perspective of geodynamics, as well as to improve on our practices in visualization, as well as co-development through ongoing community benchmarking efforts. Presentations in this series are approximately 45 minutes in length, with questions and answers following during the remaining time. These webinars are being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and presenter will have their microphones enabled, so please use the chat windows to type in your questions or to communicate with others. There's also a slight delay in the audio and video feed, so please be patient. Okay, so today we have Professor Scott King. Professor King received his PhD from Caltech and is currently a professor in geophysics at Virginia Tech. His research focuses on the dynamics and evolution of the interior of terrestrial planets and is the lead developer of the SIG-hosted code CONMAN, a finite element program for the solution of the equations of the incompressible infinite Prandtl number convection in 2 dimensions. As he has evolved beyond the game of Risk, in which world domination is its primary goal, his sights are now set on the solar system, as today he takes us off-world to show us how methods developed to study the Earth can be applied to other terrestrial planets in our solar system. In his talk, The World is Not Enough, Mantle Dynamics from a Planetary Perspective. So Scott, the floor is yours.
Thank you, Lorraine. This will be a little different than most of the other webinars that I've seen hosted by SIG, in that I'm not primarily talking about methodology, but I'm talking about using methodology in maybe a way that is somewhat less familiar to some people, obviously will be familiar to a lot of people. This is just a list of papers that I pulled more or less off the top of my head that I'm fairly certain all of these have used SIG codes in a more planetary setting. A number of these Mars, some Venus, and a couple also Mercury. There's probably a moon paper out there somewhere that I've missed, but there's quite a healthy collection of planetary science research that's being done using SIG codes. And there's 2 things that make studying other planets somewhat more different than studying Earth, in some ways challenging, in some ways not. The first of these is the behavior of the top boundary layer. Obviously, on Earth, we have plate tectonics, and the question of how to generate mobile lithosphere that behaves in a manner consistent with plate tectonics is a rich area that many people, including many people working with CIG, have spent a lot of time working on. When we get to Venus, the orange ball in the middle, there's some evidence that in Venus we have perhaps an episodic mobile lid behavior where there's resurfacing events that have taken place through history. I'm not going to talk about Venus today because there just isn't time to cover everything. And we come to Mars. We're certainly in a one-plate planet, or what we often talk about as a stagnant lid, and Mercury as well. I had the question mark here because Mercury is so small and its core is so large that whether or not Mercury convects is not an obvious answer, there's not an obvious answer to that question. What is stagnant lid convection? Here I'm showing you some plots. These are averaged at a given radius over all values of theta and phi on the sphere. The temperature structure on the right, and the RMS velocity field on the left. And what you can see is that in a sort of purplish, bluish region near the top, where we have a linear temperature gradient, where the RMS velocities go to 0, we have essentially a lid that is behaving conductively with no velocities, in other words, a stagnant lid. Below this, if you look at the pattern, this looks much more like what you would expect to see in a constant viscosity fluid. And in fact, a quite old paper by Henri Nataf and Richter showed that to a large degree in a two-dimensional case that the stagnant lid convection organizes itself such that the fluid convecting below the lid has less than an order of magnitude viscosity variation across it. This is something that Slava Solomatov and Louis Moresi have worked on quite a bit. And in fact, Slava and Louis have theoretically worked out the regimes in which, as a function of Rayleigh number, and on the vertical axis, we have a viscosity contrast. Regimes where regime 1 down there at the bottom, we have a highly mobile lid, almost like constant viscosity convection. We have sort of a transitional phase, and then we go into the stagnant lid regime above that. And we'll come back to this and talk more about this in terms of application as we go on. The second thing that makes studying planets other than Earth somewhat interesting and somewhat different is, of course, we have a variety of core sizes, and essentially a ratio of core size to planet size varies across the body that we're looking at. Here we see a figure taken from Regner and Woolley at Lunar Planetary Institute, and I just point out that that Mercury, even though it has a thin shell, it's even thinner, we know now, and that will come up, and we'll talk about that as we go on. So what I'm going to do in the rest of this talk is I'm going to look at these two different phases, the stagnant lid and size of the core, and I'm going to give you one example from my own work of how this affects what we're seeing. And then at the end, I'm going to give you my personal wish list of what I'd like to be able to see in terms of software development and where that would be interesting to go from my point of view. And so hopefully we can get there before I put everyone to sleep. So we go first to Mars, right? I'm showing you a hemisphere of Earth. You're all familiar with. I'm going to show you Mars in the same topographic scale. We're looking at the hemisphere of Mars that has Tharsis, the large volcanic province that basically you're seeing almost in the middle of that sphere, with the Tharsis Monte volcanoes sort of lining up, just trying to bait geodynamicists into coming up with an explanation for why they're so linear. And then very much off to the edge of that large topographic bulge, we have Olympus Mons. In the north, you see the northern lowlands, area of low elevation, the southern highlands, and the region separating those two is often referred to as the crustal dichotomy. And we'll come back and we'll talk a little bit about this as we go along. So let's look at both hemispheres of Mars now. We have the Tharsis hemisphere that you saw in the previous slide, and then the opposite hemisphere with Hellas Basin in the southern half of the hemisphere and Utopia. You can barely make out as the dark with a somewhat lighter ring around it in the northern hemisphere. And next to that, we have a little volcanic province called Elysium, which I will come back to and talk about. Very often when we think about volcanism on Mars, our attention immediately turns to Tharsis and the Tharsis region. And we sort of neglect to think about Elysium. But Elysium has flows, individual flows on Elysium cover the same area and have the same volume as individual flows within the Columbia River flood basalt province. So even though compared to Tharsis, Elysium is very small, it has major flows and major eruptions in its own right. And this is something I think we need to give a little bit more thought to. So, just to put the stage for those people who aren't used to thinking about Mars, this figure is taken from Todd Radcliffe and David Baker, both, by the way, former students of Jerry Schubert's. And their wonderful little book called 50 Most Extreme Places in Our Solar System. It illustrates, here we're looking at in green, the big island of Hawaii with Mauna Kea, and the peak height of Mauna Kea to the base of the seafloor is on the order of 10 kilometers high. There you can see to the left in white Mount Everest, rising about 9 kilometers above sea level. And you can't even see all of Olympus Mons in this entire image. It goes off both sides, but you get a sense of the scale, which you perhaps don't necessarily get when you look at this picture or you look at a global map. Olympus Mons is an enormous structure. Another way to look at it is a superposition of the Hawaiian Islands. The center, you see the big island, and coming off to the lower left, you see Hawaii and Maui and Oahu, Kauai. And beneath that, in the large sort of semi-transparent structure that you see is the structure of Olympus Mons. So you can see relative how large a structure this is relative to something that maybe we can get a better grasp on. An enormous volcanic structure. Well, how did Tharsis form? We could certainly take one idea from Earth in terms of a deep mantle plume, the deep mantle plume bringing heat up to near the surface, coming into melting and something like this. Of course, on Earth, we have plate tectonics, so plates move. We get chains of volcanoes. On a one-plate planet, it's not entirely clear how that sort of picture evolves. Again, taken from Baker and Radcliffe, maybe sort of visualizing what many people, I think is going on. Someone with much more graphics ability than I have has taken one of Walter Kiefer's spherical axisymmetric models of a plume formation with the red stuff being hot and the yellow stuff being sort of average temperature, the blue being cold, and superimpose that on a cutaway view of Mars so that we get a sense of the idea of a plume coming up underneath Olympus Mons. The figure itself is a little bit interesting in the sense that if you talk to Walter, he would tell you he thinks there's multiple plumes under the Tharsis region, but that's more detail than we need to think about at this point. So from this, and for quite a long time, this is a paper from the 1990s, we figured out how to make something like a single plume in a Mars-like body in convection. This is the paper by Harder and Christensen. And I draw your attention to the area that I have shown in yellow, that they get to a single plume somewhere between 5 billion and 7 billion years after the start of the calculation. Oops. Given that the Earth is, our solar system's a little over 4.5 billion years old, we obviously have a timing issue here. Without going into a whole lot of detail, their particular modeling used a small core, and so they had the transition between olivine and wadsleyite occurring just above the core mantle boundary, and this is it's the phase transformations that partly give rise to the narrowing of this structure down to sort of a one plume or degree one type structure. This is something that James Roberts and C.G. Zhang have worked a lot on, and they have a number of papers. In this paper from, I think, 96, they show starting with, in the upper left-hand corner, some sort of semi-stable equilibrium multi-plume configuration as their initial condition, with a viscosity contrast at about somewhere near half of the depth of the mantle, a viscosity increase. They're able to effectively generate a one plume or degree one type of model on the order of 250 million years of evolution. Something that looks much more promising in terms of applying this, this to Mars. And so they have a number of papers where they've worked out the conditions for this, and they talk about this both in terms of the dichotomy and later papers in terms of the formation of Tharsis. But I want to return and point out, and this is a figure from Werner's compilation of crater ages on various flanking volcanoes and volcanic structures on Mars. And she shows the region on the right of this figure being the different volcanoes on the Tharsis Montes. And it shows estimated crater ages for differing flows on these volcanoes, going up to on the order of several hundred million years ago. The area that I've circled on the right is this area Elysium, which again in the little two globes down on the lower left-hand corner, I've circled Elysium to remind you what we're looking at. And you can see that Elysium, according to the cratering ages, has been active as recently as Tharsis has been active. So there's certainly evidence that there's more than simply a single plume on Mars, if we're going to assume that both Elysium and Tharsis formed by a plume, if not some other mechanism, but there's certainly more volcanism on Mars than Tharsis alone. Another of the challenges that comes up, if we think back to the dichotomy, is that And this is based, what you're seeing on the top is a tank experiment by Wenzel, Manga, and Jelinek. And one of the things that they show in this work is that when you have an insulating region of the convecting system and a less insulating region of the surface, the blue bar across the top of their tank represents the area of insulation. What you get is an upwelling that forms under the area of insulation. They do a sketch to show what they envision happening on Mars below. If you think of the southern hemisphere as perhaps having a thicker lithosphere than the northern hemisphere, that's not entirely obvious that that is the case, but if we make that assumption, then you would naturally, by application of this tank models and other experiments as well, expect that the upwelling that would form would preferentially form underneath the thick hemisphere or the thick lid and not under the thin lid. This is a calculation of my own, and where I've again imposed a thick hemisphere in the form of a high viscosity layer under one half of the model, the lower half, and a thin hemisphere under the other half, and superimposed on top of that the Tharsis or Mars topography, just to sort of give you a vision of what you're looking at. The Tharsis Monte volcanoes are over there near the edge of the left side of the sphere at that point. And so what you're seeing underneath that in orange is an iso surface of constant temperature of hot material coming up preferentially underneath the thicker hemisphere. And so the question is, how do we get from that situation to what we see on Mars today, where the Tharsis region almost straddles the boundary of the dichotomy between the thick and thin hemisphere. It's not exactly where the dichotomy is under Tharsis is anyone's guess, but you can suggest that based on the tank experiments, based on the numerical models, this is not where you would expect a large plume to form. Again, C.G. Zhang has worked on this problem, and he's actually shown that in the thick hemisphere, thin hemisphere model, he sort of shows the thickened hemisphere in this bluish grayish color above the core, that with time, this hemisphere, or depending on how you want to look at it, what frame of reference you want to look at, the plume migrates relative to this hemisphere along the boundary or toward the boundary of the thick, thin hemispheres. And the physical explanation for why this happens, I don't want to delve into too deeply at this point. But it's a very interesting suggestion, because it would suggest that perhaps the plume did come up somewhere underneath the southern hemisphere of Mars, and with time has migrated toward its present location, or if you prefer to think of it that way, the crust has migrated to its present location, depending on what frame of reference you want to look at. This has been followed up by Andrei Sarnek and CG in a couple of other papers as well, again illustrating what they see happening over, as you can see in these figures, a rather short period of time of 150 million years in this particular model. We began looking at gravity and topography on Mars, trying to understand the crustal thickness. I originally got interested in this problem because I wanted to strip the crust off and look at the remaining gravity signal below the crust. And so we began learning how planetary science people begin to develop crustal thickness models. And in the process of doing this in Karina's work, she developed a model that you see here that fits the gravity and topography. And we actually see a region of thickened crust that extends from almost underneath the South Pole, kind of following the track there through the large part of Tharsis, all the way up perhaps as high as Alba Patera, the northernmost of the shield volcanoes. It's very interesting because one would imagine that if the plume had migrated from the South Pole to the region where we see Tharsis now, that we might see crustal underplating or regions of enhanced volcanism and so forth along a path of this region. And that's indeed what perhaps Karina's models are showing from this track. But one of the things that I began to think about doing at this point is saying, let's see if we can use the geologic history of Mars to be consistent with these geodynamic modeling. We can certainly create models that create a low degree structure, a degree 1 or degree 2 type structure, but can we take a convection model from somewhat hot beginning early in the history of the planet, run this forward, create a Tharsis anomaly, and then have that continual stream of small volcanic activity that would be consistent with the flows in the diagram by Werner that suggests that there have been flows episodically but somewhat continuously from the time Tharsis formed almost to present day. So can we produce Tharsis rise, but then continue to produce a small amount of volcanism? And so that is something that we've been working on. We began starting by looking at some of the two-dimensional work that had been done. And the plot you see on the left is a model in axisymmetric geometry by Walter Kiefer. You see the color scale below indicating temperature. And what you see is along the axis of symmetry, and this is a spherical axisymmetric model, so you can envision rotating the model around this plume in 3 dimensions to get a 1/2 of a hemisphere. What you see is a thermal structure with a blue to purple to black stagnant lid. And right at the top of that plume, what you see in white, white is not the temperature, but white is actually a small amount of melt that's being produced in the model. Now, we began looking at this, and we tried to represent what Walter was doing in 3-dimensional spherical geometry instead of axisymmetric. And the funny-looking blob that you see on the right in blue is actually a hot isosurface of temperatures where we have used the same parameters that Walter used in the axisymmetric model. And one of the things, and we've known this for a long time, axisymmetric models tend to produce a very large upwelling right along the axis of symmetry. And then the further away you get from the axis of symmetry, the more what you're actually seeing is a sheet that is a small circle about essentially the pole, which is where the plume is. So the blue things that you see there are not really individual blob-like downwellings. They actually represent, in terms of the physics of the equations, they represent a sheet that follows a small circle in that case. And so this geometry, simply because Walter was able to produce a single upwelling with one plume structure that produced melt here, if we translate the exact same parameters into the spherical model, we end up getting something on the order of 15 or so plumes in this model. And because each plume is drawing from sort of a smaller region of the core mantle boundary, the individual heat being brought up by each plume is smaller, and hence you don't get melt. And so this is one thing that we see, and maybe one of the reasons that we need to be moving into three-dimensional modeling for this sort of thing. I'll point out here, and this will be on my wish list at the end, but what we're doing is we're using a very simple melting formulation. We do feed back the latent heat of melting into the energy equation. But once we have melt, we do what many people have done over the years in geodynamics, assume that melt immediately gets to the surface, and we don't track that melt any further. So in other words, once a region has melted, it could come back around and melt again as though it were fresh, fertile mantle. We certainly know that's not the case, and people are really beginning to push melting formulation much further now. But this is a challenge doing this in a three-dimensional spherical geometry. So we use a simple formulation. We use a solidus taken from the literature based on the Martian meteorites. And we have a fairly simple melting formulation that says for every degree above the solidus we create about 0.05% of melt. And then, as I said, we immediately take that melt to the surface. So I'm going to show you a couple of models now. And what I'm showing you in this plot is the amount of melt that's produced as a function of time. And I'll show you in a few minutes that we think Tharsis was almost completely formed by 3 billion years ago. It formed, obviously, after the crustal dichotomy formed. People put the formation of the crustal dichotomy now somewhere between 4 and 4.2 billion years ago. And so we began looking at this, and the amount of melt that we would need in terms of cubic kilometers per year for, say, 300 million years in order to produce Tharsis is way down on this graph, somewhere below 15 or 20 or something like that. So we don't need, we're producing in this particular calculation an enormous amount of melt, right after the beginning of the calculation here. If we go to a Rayleigh number of 10 to the 7th, we delay the onset of when we produce the melt, and we produce a somewhat less melt, and that we felt we understood very well. And then we got the following, 10 to the 6th. And we first looked at this and said, this is rubbish. We don't think this can possibly be right. But on further reflection and recognition of what's going on, we actually come to recognize that, in fact, indeed, this is right. And that when we're thinking about melting in these models, we have to be careful because the melt is a combination of two things, which I will show you next. Interestingly, when we looked at the timing of these peaks and we compared them, the timing of the peaks are consistent with the time scale for an instability to form at the core mantle boundary, based on a paper by Peter Olson and colleagues in the late 1980s. And so this fits very well. And in fact, what you see, and we go back and look at the models in detail, these peaks occur when the first large degree 1 type plume is rising and reaching the surface of the Earth. So the peaks themselves correspond to the arrival of the plume after formation, which is somewhat of an interesting thing. It says perhaps we can use the timing of when Tharsis began to say something about the fluid dynamics of the Martian mantle. But let's look at this crazy Rayleigh number 10 to the 6 case here. And one of the things that we had to do is go back and look at this, is look at the fact that as you have a stagnant lid, the thickness of the boundary layer increases with decreasing Rayleigh number. So you see the arrow going up. Perhaps the arrow should be going down. It doesn't really matter. But what you're seeing are boundary layer thicknesses, and we calculated this by calculating the inflection point of that radially averaged temperature profile, which is what you're seeing in the upper left-hand corner, and the arrows pointing there essentially at the inflection point. We measure that inflection point as a function of, in each one of these models. And you can see that actually, as the model evolves, that a boundary layer gets a little bit thicker. But actually, very early on, these calculations set the boundary layer thickness very close to what ends up being the steady case. And we're assuming here that the base of this thermal boundary layer represents the pressure at which this plume head is going to reach the mantle or reach the lithosphere, and it's going to control the pressure of melting that we see. So actually what we see in this case is that the very low Rayleigh number calculation has an enormously thick lithosphere, which is not surprising at all, and that that melting would occur unless this plume is actually eroding into the lithosphere. Melt would occur at extremely deep depths. What is also happening in stagnant lid convection, because as the lower Rayleigh number we go, the thicker that lid gets, the less heat can get out, the higher the average mantle temperature is. So what you can actually see is that the low Rayleigh number case in blue has an average mantle temperature that's almost 400 degrees hotter than the high Rayleigh number case. And so it's the melting requires both pressure and temperature, and changing the Rayleigh number has opposite effects on pressure and temperature. So if we could systematically sample these basalts on Mars, we would actually have a chance of looking at the pressure-temperature relationship here. The depth of melting is something geochemically we could look at. But in terms of melting, this explains why if we get to a very low Rayleigh number case, essentially because the system essentially becomes so insulating at the top that because of the internal heat being generated in the model, the mantle just heats up with time. So these are isosurfaces from these calculations showing you sort of what you're seeing at the time, shortly around the time that these plumes hit the lithosphere. And so what you see in the Rayleigh number 10 to the 8th case is red, which indicates where we have melting. Two of the plumes in that 10 to the 8th case actually produce melt. The others don't. When we get to the 10 to the 7th, we sort of have a sheet-like upwelling with a plume here. This is something that you can see if you look back in Roberts and Zong's papers that they talk about there. If you look at the 10 to the 6th case, we basically have melt everywhere. It's very deep, but it's very hot, and we basically have a layer of melt at 500 kilometers depth. But one of the intriguing things about this is that not every plume in these models generates melt. So it's not impossible that one has several regions on Mars where one has plumes that are large enough to generate melt, and one could have other plumes on Mars that don't generate melt, that aren't strong enough to generate melt with time. And so, perhaps the degree 1 structure is not absolutely necessary for this formation. So, the periods here, this is a sort of a geologic history map or figure from Mars with the 3 Martian epochs, the Noachian earliest period being essentially right after the dichotomy forms. You can see that by 3 billion years, we expect that most of Tharsis is formed, yet the evidence from the cratering is that there's a small amount of volcanic flows that continue, perhaps to very recently. And so, again, part of what we were looking at is the question of, can we produce a huge amount of melt from that first upwelling plume, have that generate most of what we need to form Tharsis by 3 million years ago, but continue to have a small dribble that continues on to present. We thought of 2 ways of dealing with the fact that the planet is cooling down, or what we're basically thinking about is the fact that the planet is cooling down. We can decrease the core mantle boundary temperature, which we believe is happening, and we need to, if we're looking over the entire history of the planet, worry about decaying heat sources. Both of these are about 5 lines of code change to the code to be able to implement these. What you see in the horizontal lines are what people tend to do, because most of us in the mantle dynamics community grew up out of a background in fluid mechanics, where we leave heat sources as a constant term. But since in planets, heat sources come from radioactive elements and the amount of heat sources are decaying with time, the 2 curves give you estimates of 2 different estimates of the uranium, thorium, and potassium heat in the Martian mantle. The difference between the black line, Lauders and Fagley, and the Vanke and Thribus models are that the amount of potassium that's presumed to be in the mantle differs. And so that's what drives the difference in these 2 things. And so what you can see is that, in fact, we have almost a factor of 4 decrease in heat-producing elements from early in the Earth to the present, or early in Mars to present day. And the question is, can this, essentially the cooling down of this planet, explain the shutting off of the volcanic activity at Tharsis? And in the interest of time, the simple answer to that question is yes, and I won't show you a whole bunch more plots and models where we think that we can demonstrate this. But it leads to an interesting dilemma. Once melt production stops, once the planet cools such that we don't get melt, we don't get melt. So that means we can't explain the recent volcanism using the same mechanism, essentially the sort of the secondary effect of the plume through time. And we can talk about some other ways that we think we might be able to make that. And I suspect that there is a region of parameter space, of sort of a Goldilocks region, where we could actually make the parameters solve all this. But that's we're time to move on to Mercury and move on to the other aspect that I want to talk about, which is, even though Mercury, as we'll see, is also a stagnant lid, Mercury is a very thin body. And even though you might look at the two images and think, a rocky airless body with lots of craters, Mercury is definitely not the moon. There are a number of puzzles on Mercury, and with MESSENGER, I'm guessing in hiatus, thanks to the shutdown, we're collecting a lot of new observations, and things are in a great state of flux in terms of our understanding of what's going on with Mercury. But there are several big surprises. The first is that there's some areas of uplift that are almost impossible to explain without them being tectonic. And why does small little Mercury with this thin mantle have this interesting tectonics going on? And when did this happen? There's evidence for volcanism, in fact, a lot more evidence for volcanism than was ever thought before we went to Mercury. And a lot of that volcanism postdates the time of the late heavy bombardment, which, again, given Mercury's thin size and its small size, doesn't fit with sort of the live fast, die young picture of a small body. There's also the stress orientations and the pattern of stresses on Mercury, which don't appear to be random, but actually appear to be organized and suggest that something's going on. So many of these things seem to require that little Mercury had an active mantle. When and is this even possible with our known constraints? Well, for those of you who are unfamiliar, the rupees are basically thrust fault-like scarp structures. I think most people would call them thrust faults. You're seeing one of the larger rupees on the planet Mercury. It's over 550 kilometers long. It's called Discovery. The arrows show you what's going on. You can see that it cuts craters, and so it has to be younger than many of the craters. And again, the timing of the rupees is rather interesting, because if you think all of these compressive features are telling you about contraction of the planet and global contraction, you don't see these things in the oldest features. You see it in some of the younger surfaces. And so where is the old compression that should be going on? And so there's issues there with timing that I'm not going to go into, because I'm probably not the right person to be talking about that. But we've got evidence for this compression. And this is something that, again, I began playing with Mercury a number of years ago, and discovered that in a thin body, you tended to get a different type of structure than what we're normally used to seeing in spherical bodies, where we see plumes. You tend to get more elongated linear features, and sometimes these things go into more hexagonal patterns and at those boundaries. And this got the attention of some of the people who were mapping out these structures. This is a map by Tom Waters. That's his most up-to-date map from this spring's Lunar and Planetary Science meeting. And you can see that there is a sense to which a number of those black lines, which represent the mapped thrust fault features, have a north-south orientation, sort of in the mid-latitudes of the planet. And many of them are very short. But you can see that there's a very clear east-west pattern to these things in the very low latitudes. The very light yellow colored that I hope that you're able to see is the volcanic material in the northern volcanic plains and volcanic material in Hellas or in Caloris Basin, and you don't see an awful lot of compressive features there, and whether they're underneath the volcanics or not is an interesting question that's beyond my set of skills. So, a bigger picture of the lobate scarps, but this is the thing that caught my attention when we started thinking about Mercury, because if this was all due to planetary contraction, there should be no orientation at all to the faults. They should be completely random. And the fact that we saw something in the lower latitudes and something in the high latitudes was consistent with this pattern that we saw in the rolls in convection. This is a recent paper by Zuber, and we're looking again at a topography map. Because of the orientation of Mercury, we're not seeing that very much in the southern hemisphere. We lose that control. But what I want you to see quickly is that the red areas, the topographic highs, cut through, in many cases, the impact craters. The big circle there near the northern, or the 180 of Mercury, there's one called Mozart, a large impact crater, and Caloris, which is one of the largest multi-ring basins we've mapped in the solar system. And you can see that the topography, you don't see the topography of the impact crater at all. In fact, you see topographic highs that cut through it. So obviously this topography postdates this, and what is the source of this topography? You can also see this is another view. Here we're looking at the northern hemisphere once again, and the volcanic plains are outlined in black. In the middle of the northern volcanic plains, you see somewhat of a topographic high. And you see topography, again, that cuts through the Caloris Basin, and as well as these linear topography features that admittedly are covered with craters, but you do see some structure within this topography. We don't have much time to go on with that, so I'll just remind you that there are at least 3 types of planforms you see in convection in a spherical shell. There's something like the degree 1 patterns. They're low degree patterns that Zhang and Roberts talked a lot about with Mars. In thin shells, you see these rolls, and what we're most used to seeing are sort of multiple plume orientations. This is a series of calculations where I varied the thickness of the spherical shell, kept the Rayleigh number fixed, and use this exact same initial condition. So in the lower right corner, you have something that's very Mars-like. The upper left corner, perhaps something more Mercury-like. And you can see exact same initial conditions. These things evolve from plume structure to roll structure. And actually, if you look more carefully, you can see that essentially the plumes form sort of at the core mantle boundary, form at the regions of connection between these linear features. That's something that actually Bercovici showed in some of the earliest 3D papers, and that actually that these features end up becoming what in the thin shell you see as the rolls. I realize we're running late on time, and I'll try and get through this really quickly at this point. The thickness of Mercury's mantle, from Mariner 10, basically from the average value of density and gravity, we came up with something on the order of a 600-kilometer thickness. Harder and Schubert used the iron sulfide phase diagram, and you can notice on the green there, they come up with a mantle thickness of 440, but plus or minus 420 kilometers thick. The recent papers on gravity from Messenger by Dave Smith and the Messenger team, using the moment of inertia values as well as gravity, come up with a 400-kilometer radius. So the mantle's even thinner than what we had thought before. And puzzlingly, a density of 3,600 kilograms per meter cubed. And you cannot find a silicate material at that low a pressure that can give you that kind of density. I'll show you that a more recent paper by many of the same authors has sort of reduced that, but the data allow still a very large mantle density. And in fact, the only way that the authors were able to constrain this or come up with a reasonable model based on this was to have a silicate shell and then a dense layer. They proposed iron sulfide above a core like this. So we're in an interesting situation where the mantle of Mercury is getting thinner and thinner, yet the evidence still is pushing us for tectonic features. Well, to move on quickly, the models that I showed you before, I only went up to a radius of 0.75. That gives me a 600-kilometer thick mantle, which no longer seems consistent with the Messenger data. Rather than running a bunch of models, I went back to Solomatov's plots of stagnant lid transition, no convection region. And there's the blue region is the 2008 paper. And obviously, if we make the shell thinner, we decrease the Rayleigh number, and we're further into the no convecting region, and it becomes more difficult to envision how you can have convection. And in fact, you do a calculation with a 360-kilometer thick mantle, you get isotherms that are spherical shells, you get nothing but a diffusive solution, and consistent with Solomatov. One way to get out of this is to go back and look at the rheology. In the Earth, we think the upper 200 kilometers of the mantle is actually controlled by dislocation creep, not diffusion creep. And dislocation creep has a power law exponent of 3. So if I take diffusion creep and I look at pressure, which here goes down 6,000 megapascals, is essentially 400 kilometers depth in Mercury, I look at a diffusion creep viscosity law like this, I in fact see that, something on the order of 10 to the 20, 10 to the 21, what we expect of Mercury is happening. If I change to dislocation creep, and here we have to worry about scaling the Rayleigh number, and we don't have time at all to talk about that. We're in the mobile lid regime again. Again, plotting this with Hirth and Kolstad, and you can see that in the temperature regime at 6,000 megapascals and say 1,400 degrees, we are in a regime where we would think dislocation creep is what would control Mercury. And indeed, dislocation creep with even a very thin shell, we get a roll-like pattern. I'm not going to, everybody always asks me whenever I talk about Mercury about hot poles, and so I finally actually did a hot pole calculation. This is the, essentially Mercury is in a 3-2 resonant rotation orbit resonance. So it actually spends a good deal of its surface in two locations more close to the sun. And if you predict what you would expect surface temperatures to be, you'd get a pattern like this. If you impose those surface temperatures on the model, you actually do find that this does seem to reorganize the pattern a little bit underneath the hot poles. This is, I've simply done one calculation and I haven't had enough time to really analyze a way through this. Anyway, what we're seeing is that Mercury has lots of puzzles, and there's certainly plenty of room to jump in and work here. Mercury's topography seems to have linear features. There's compressional features that suggest some sort of control organizing their structure. And if this FES layer exists above Mercury's core, it's dense enough to be stable, and it's really hard to explain Mercury's topography at that point any other way. So, quickly, my perspective, planets begin hot and possibly molten. I haven't talked about magma oceans at all, but this is an area that I think we'd really like to see some more work developing here. If we're going to deal with particularly Mercury and Mars, a lot of the interesting geology happens right at the time or soon after formation, and it may continue until much more recently. So we need to worry about core temperatures that decrease with time and heat sources that decay with time. And if I came up with my wish list, and there are certainly people working on this, but we would certainly like to see a better thermodynamic melt formulation. This gets into multi-scale physics, some of the things that Mark Spiegelman gets very excited about. And this could be an area where I think CIG could play a constructive role here. We also, obviously, and we're certainly not the only ones, everybody would like to see more robust solvers, particularly when we're dealing with nonlinear rheology, and certainly Mercury makes sense, and ice rheology is another case where this makes sense. If we're going to feedback melt into rheology, then we're also going to have very localized effects there, and so that's another area. We have to worry about how to accurately advect melt, and then of course there's resolution. And at the risk of being a little bit provocative, I put together the following grid scenarios. Basically for Mercury and Mars, I've been using something on the order of 65 nodes in the radial direction. That's probably good enough. For Venus, certainly we'd like to be at 97 or 129, something like that. And if I based what I would like to do for an Earth-like model on my 2D work, then we would need at least that 2.8 kilometer global resolution. And you can begin to see how many unknowns, if I assume I need to store 3 velocities, temperature, pressure, and viscosity, we're up to an outrageous number of unknowns and more cores than anyone is going to give me for enough time to deal with this. So I just mentioned that, of course, CIG is working on adaptive mesh refinement, and regional problems can be done with sitcom CU, but when I look at this graph and I look at where we would like to go, it gives me a little bit of pause. And so I will end there. I'm sorry that this took longer than I thought, but this is probably the last time I'm going to try and talk about 2 planets in one talk because there's just too much to cover. So thank you very, very much for sticking with it.
Great, thank you for sticking with us as well as we try to get through our problems. If anybody has any questions, please go ahead and type them into the chat window as we're wrapping up here. I have one question for Scott. I was curious on about what codes you use to do your work with and how you would contrast working on terrestrial planets versus Earth in any sort of different differences in model setups or things you have to consider.
Well, we're using Sitcom S primarily at this point. And, you know, in some ways, life is a little bit easier because in stagnant lid, we don't have to worry so much about resolution near the surface. And, you know, we don't have to worry exactly about the details of subduction, which is a problem that many people working on the Earth are spending a huge amount of time working on. So in some ways it's easier. That also means we can get away with lower resolution, and that may be one reason I've been drawn to work on Mercury and Mars, because we actually had the better resolution to work on now. How would an impact origin of Martian topography change thermal evolution of Mars, assuming the impact theory is possible? Lee Jun. Good question. James Roberts has worked on that a little bit. Even the large enough impacts to form some of the northern lowlands are not going to be enough to significantly. I think James originally was looking at it from the point of view of would this impart enough heat to the core to shut off the dynamo. And the conclusion there was that it's simply you couldn't get enough heat that far deep into the mantle. I think it's a very interesting possibility. Specifically in the modeling we've done, we've kind of assumed that the dichotomy was there and already formed, simply because the physics of dealing with imparting that heat is somewhat interesting and sort of beyond what we were ready to tackle at that point. But I don't think there's enough to totally change the picture. Okay. Well, if there are no other questions, then I thank everybody for participating
Great. Well,
in
we
the process.
see if anybody else is typing in more questions. I want to remind people of our next webinar. Our next webinar is going to be on November the 14th, and it's actually going to be at noon. That is 12 o'clock Pacific time. Our speaker will be from Italy. He'll be Giorgio Spada from the University of Urbino, who will introduce us to the new SIG code, not SIG code, the new code in our repository, Selene, which can be used to predict geophysical measurements in response to glacial isostatic adjustments. Okay, I don't see any more typing. I want to thank Scott once again for his time today and for giving us a really fascinating perspective on the interior of the terrestrial planets. Thanks a lot, Scott.
Well, thank everyone for listening.